Quality testing at the point of manufacture assures that the product meets specifications. While that is important, it is essential to ensure product reliability, especially when it needs to perform over extended periods of time. Consider a situation where 1,000 bulbs are being tested by keeping them switched on continuously. After every week, the number of bulbs failed is counted. Let us say the rate of failure is constant. At the end of the first week, 13 bulbs would have failed, leaving 987 bulbs. In the next week, another 13 fail, and we are left with 973, and so on. The graph shows the bulbs surviving as a function of time elapsed. At the end of 10 weeks, it is 875, and after 50 weeks it goes down to 513. Since the failure rate is constant, the number of bulbs surviving at any time t can be calculated using exponential distribution. In real life, failure rate remaining constant is rather uncommon. It either increases or decreases. The instances of reducing failure rate is characteristic of situations where the failure rate initially is high and it drops over a period of time. Infant mortality is an example of this. Often electrical components like resistors and sensors also show this kind of nature. We will discuss that in more detail in a future video. In most cases, however, the rate increases with time, as is natural when something undergoes wear and tear. Now let us see how this relates to our earlier example. When we have a situation where the failure rate drops over a period of time, the graph of failure rate versus time shows a steep drop. Using that, we calculate the number of bulbs left over after each time period. At the end of 10 weeks, the remaining bulbs drops to 772, much lower than what we saw for the constant rate case. But the rate of failure drops over time, and about 467 bulbs are left at the end of 50 weeks. So essentially 305 bulbs failed between the 10th and 50th weeks. In comparison, for a constant failure rate, for the same period, 362 bulbs failed. Increase in failure rate over time is easier to relate to as it is a result of wear and tear in use. The graph of failure rate versus time reflects the trend. Expectedly, the number of bulbs that survive 10 weeks of use is the highest of the three at 952, but by the end of the 50th week, only 580 survive. So while the failures initially was lower, between the 10th and 50th week, 372 bulbs failed, which is the highest of the three cases. Okay, let us now bring all this together. In real life, for any product that we use over a period of time, all the three phases occur. The first is the break-in phase, and it is generally recommended to start slow and gradually increase the load at this stage. This is usually a very small period and more a customer's judgment on when they feel they can start increasing the load. The second phase is the useful life. During this phase, breakdowns are not expected, and in rare cases when they occur, they are chance occurrences. The third phase is when it nears the end of its life. After a certain level of usage, significant wear and tear would have happened, which could cause a breakdown, and the probability increases with time. Earlier, we talked about using an exponential distribution to analyze reliability of constant failure rate systems. If the failure rate varies with time, we use a Weibull distribution instead. So, we have just covered the basics of failure rate and kind of quantified what it would mean if the failure rate stayed constant or it changed with time. In the next video, we will see how they can be characterized and what insights we can get from them. See you then.